Alright, in today's lesson you are going to be finding the area in between two curves. With your knowledge that you already have of calculus and the area under a curve, we're going to use that and apply it to find area in between two curves, or another way to say that is bounded by two curves. So for example, these two curves that you see here create an area in between them. That area is bounded by the two curves. We can find that area using some general concepts of calculus that you already have, aka the definite integral. So using the knowledge that you already have, think about this. If I can find the area under this top curve here, and then I can also find the area under the bottom curve as well. You should agree that if I take this total area and subtract out the bottom parts, I will be left with the area in between the two curves, or the area bounded by those two curves. It's a very easy concept to understand. We'll just have to use some of the knowledge that you already have of calculus and the definite integral to solve some problems. So, with that being said, we'll take a look at a definition. Alright, area between two curves. As usual with calculus, you need to have things that are true. For example, the two functions have to be continuous. F of x has to be greater than or equal to g of x. Throughout the interval, it's a closed interval from a to b. So, let's put that in English very quick. From a to b, one function, and we'll call that top function f of x, has to be greater than or equal to the bottom function from a to b. If that is true, then we can use the area integral here. It's a definite integral from a to b, and what we'll plug in is the top function, f of x, minus the bottom function, g of x. And then all we're going to do is use our knowledge that we already have of definite integrals to find the area in between the two curves. So, take a look at an example. Alright, for our example, we have find the area of the region between secant squared x and sine of x from 0 to pi over 4. Now, before you do anything, you have to make sure one function is greater than or equal to the other function from a to b. Or in this case, a is 0, b is pi over 4. So in order to do so, we can take a look at a graph. So looking at our graph, I have our equations in already, and as you know, secant squared x is 1 over cosine squared x, and in y2 I have the other function sine of x. We need to make sure one of these functions is always greater than or equal to the other. Looking at the graph, this is the first function graph. It is secant squared x, and the other function is sine of x. And you can see from the graph that secant squared is always greater than sine squared. So with that being said, they are both continuous on this interval from 0 to pi over 4, and one is greater than the other. So we can apply our definite integral formula. The area between the two curves is given by the definite integral from a to b, 0 to pi over 4, of f of x minus g of x. Now our f of x is our top curve every single time. Our top curve in this case is secant squared x minus the bottom curve, which is sine of x. That is simple. Now if it's a calculator active portion of your test or homework, then you can plug that in the calculator and find that value. If it is not, we will anti-differentiate and use the fundamental theorem of calculus to find the area. So, doing that, let's go ahead and find the antiderivatives of each of these and apply the fundamental theorem of calculus. This area would then be equal to antiderivative of secant squared x is tangent x minus antiderivative of sine is going to be cosine. And we're going to evaluate that from 0 to pi over 4. Now, we'll go ahead and simplify from there, and we should be absolutely fantastic. So simplifying, we will take pi over 4, the upper limit, and insert it into our expression. Tangent of pi over 4, you know, is a value of 1, plus cosine of pi over 4 is square root of 2 over 2. And we're applying the fundamental theorem of calculus, so we subtract this. Tangent of 0. Well, tangent is the y value over the x. 0 has an ordered pair. Just to remember our trig and our unit circle, at 0 we have an ordered pair of 1, 0. So it would be 0 over 1, which is 0, plus cosine of 0. Cosine of 0, you know, is 1. We now simplify. 1 plus the square root of 2 over 2 minus 1. So we have 1 plus square root of 2 over 2 minus 1. 1's cancel, and you have an answer of the square root of 2 over 2. Now that is an area in between two curves. The area in between two curves, if we want to put units on this, we are always measuring area in some sort of units squared. Since we didn't have units in the original problem, we can just call them units squared. So the area in between these two curves is pi over 2, square root of 2 over 2 units squared. Okay, now we are going to be given two equations. We have y1 and y2. One is a parabola with a negative leading term. The other is a line with a negative slope. You can see that if we want to find the area enclosed by this region, we have a top curve here and a bottom curve, which is the line. They enclose this shaded area. Now we can find that area with the same formula that we have used up to this point. The only problem is we do not know what x values to integrate from. We need that value and that value. They will be our a value and our b value, or our upper and lower limits of integration. So, once again, if it's calculator active, go ahead and use the calculator to find the intersection. If it is not, you will have to find the intersection of those two things algebraically, which in this case is pretty easy. If I want to find out where these two functions meet, I will find out where they are equal, or set them equal. So I have 2 minus x squared equals negative x. Solving that so that we can find out where they equal, it would be 0 equals x squared minus x minus 2. That is a quadratic that factors. It will factor into b negative 2 and a positive 1. That is our factored form. Finding out their intersection, you should agree that we have an x equals negative 1 and an x equals 2. So our x values, where they intersect, they intersect at negative 1 and 2 on the x-axis. They are the lower and upper limits of integration. Once we know those, we can use our algebra and the definite integral, along with the fundamental theorem of calculus, to find the value. So, applying the formula for the area between two curves, the area is given by our lower limit of integration is negative 1. Upper limit is 2. Now we have the top curve minus the bottom curve. The top curve is the parabola. 2 minus x squared. Minus the bottom curve, which is a negative x. And of course, we have to have our dx. Now, simplifying from there, we'll go ahead and find the antiderivatives. We will use the fundamental theorem of calculus to find the exact value of the definite integral. So, before we do any of this math here, I think it's easier to simplify what is inside parentheses first. That is equal to the definite integral from -1 to 2. I have a negative x squared. This becomes a positive x and a positive 2. Now we have it in a little bit easier terms, I think, to deal with. We can go ahead and find the values from there. Here we go. Antiderivative of negative x squared is negative x cubed over 3 plus x squared over 2 plus 2x. All of that is evaluated from our upper and lower limits, -1 to 2. And from there, like I said, we're applying the fundamental theorem of calculus and simplifying. So substituting in a 2 and then subtracting, substituting in a 1. So we have 2 cubed, which is 8, so it's -8 over 3 plus 2 squared. 4 over 2 is 2, and plus 4 minus -1 cubed is -1 with a negative out front, so that becomes 1/3. -1 squared is 1, so it's plus 1/2. And this is a -2. Now, all we need to do from there is go ahead and simplify. And once you simplify those things, you should come up with an answer of 9 over 2. And as we said before, it is an area. Area is always square units. So we have units squared. This area between two curves. If you do not know the upper and lower limits of integration, you must find them. If it is not calculator active, set the two things equal to find their intersection. They are the x values that are the upper and lower limits of integration. Once you have those, top curve minus bottom curve. After you have that, then once we get here, we're just using all the knowledge that we already have, which is the knowledge of definite integrals and finding their exact value with the fundamental theorem of calculus. Okay, so the next one, we're going to use a calculator to find the value. So, it says find the area of the region enclosed by the graphs of y equals 2 cosine x and y equals x squared minus 1. We will find the values in the calculator. So I need to know which curve is the top curve, which curve is the bottom curve, and make sure they are consistent throughout. So, if I go ahead and enter these into y1 and y2, it is 2 cosine x and x squared minus 1. Alright, here's our first curve. It is the cosine curve. And the next curve is the parabola. We can find the area of the region enclosed by those two things. I better get a marker. The area enclosed is this area here. Now, simple at this point. We know the top curve and the bottom curve. That is fine. The only thing we don't know are the upper and lower limits of integration. We need the x values, where we're going to integrate from. So we can find the intersection of those values or those curves on the calculator, and we've done this a million times. You can hit second trace and go to intersect number 5. First curve, second curve, and I will get it close with a guess. Now, you're going to see that the calculator gives us a decimal. This value is something we do not want to approximate to be accurate. We do not want to approximate a value in the middle of a problem. You do not round or truncate until the end. So, with that being said, we need to store this value in a variable. Go directly to the home screen and hit the store button, and I'm going to store it in letter A. That way it will store the whole thing. We're going to do the same thing to find the upper limit, B. Go back to the graph, second calculate, intersect. And make sure your guess is over by the B so that it chooses this intersection. And I will hit enter. It will give me the X value, and you see once again it's a crazy decimal. We do not want to round that. You want to store it. Go directly to the home screen. I'm going to store that in letter B. Now, our A and B are our upper and lower limits of integration. So, using that, we know the area between the two curves. My lower limit I've already stored in the calculator. It's there. So we do not want to round. We're going to use the actual value. So the lower limit was A. The upper limit was B. That is the letters I stored in the calculator. Then we need the top curve minus the bottom curve. Our top curve in this case is 2 cosine x. 2 cosine x minus the bottom curve, x squared minus 1 dx. That is what we will find in the calculator. Now, what you need to be careful of is we need to actually integrate the top function f of x minus the bottom function g of x. So we can't just integrate on the graph that we have now. So what we're going to do is, one way to do it is in the calculator, if I have the top function and the bottom function entered, I can use function notation in the calculator and do y1 minus y2. So if I turn those off and we just take a look at the f of x minus g of x, this is y1 minus y2. We want to integrate that from a to b. So, doing so, we can go second calculate and go to our number 7, which is the definite integral. It asks for the lower limit. Our lower limit we have stored in alpha a, or letter A. Our upper limit we have stored in letter B. And it will give us the actual value here. So, if it's calculator active and we assume that this question was, we would say, as long as you show this, you are fine. You would say that the area is 4.995. That is rounded to 3 decimal places. That is units squared. Now, on an actual AP test and on your test that you have in class, I want you to show about, I want an approximation of what A and B are. If you write down their approximation, we will be fine. So you could say something like A is about, and I believe it was negative 1 point, let's double check here, 1.265, and B is about 1.265. Have those on your paper so we can see an estimate of what your upper and lower limits of integration are. Then we can type everything in the calculator. That is from the graph. You can also find that area at the home screen on the calculator. So if we use the home screen, you can see I'm at the home screen there. When we're at the home screen, we can still find the values of definite integrals. You'll hit Math, as we have before, and you will find number 9 on this calculator anyway. We're going to integrate a function. So, that is our integral. 2 things. You can type this in by hand, or since I have it stored in y3, I can go through the normal function stuff and find y3. So let me go back to the home screen and I can enter y3 there. Then, we want to integrate y3 with respect to x. And then it asks for your upper and lower limits of integration. My lower limit was a, comma, my upper limit is b. And then you'll close your parentheses. And when you hit enter, it shouldn't say go to. It's because I cleared y1. Devastating for me. 2 cosine x. Then let's go back to the home screen. And you can see that we come up with the exact same value as we did previously. So just make sure if you're going to use this way with the function notation, when I went through and hit the wrong button, I cleared y1. Your y1 and y2 have to be in perfectly because we have y3 stored as y1 minus y2. We're using a lot of function notation there. If you don't like to use those y1s, y2s, and y3s, you can do the same thing, except in this spot you need to type in the actual function. So that's some good calculator practice, if nothing else. And there's our answer. We rounded to 3 decimal places. Alright, now for example 3, we're given 2 equations and we want to find the area between those 2 equations, and we're going to use the calculator again. You can see that I have, in my y equals, I have the square root as the denominator in y1 and the 4th power polynomial in y2. And one way you can tell the difference between the two is I went ahead and made the y2 the darker line or the thicker line. That way when you graph them, you can tell the difference for which one is the top and which one is the bottom. You can see that the bottom curve, after they intersect, and the area bounded is somewhere around there. Looks like 0, but we need to verify it. And up to this point on the x-axis, this will be our A, and this will be our B value. So we have the bottom curve is the darker one, which is the polynomial, and the top curve is the thinner one, and we will go ahead and follow the same process as we did before. In order to find the value, we need to know the upper and lower limits of integration. We'll store those in A and B as we did before, and then we'll let the calculator do the work in this case. So I will go second trace and find their intersection. The first intersection you can see is 0 on the x-axis, so that is A. A actually in this case is a whole number, so A is 0. And then for B, we can find B by doing the same thing. We're looking for the intersection. Make sure when you guess you get the cursor over closer to that intersection so the calculator knows which one you're finding. And you can see that this one is some crazy decimal. So we're going to use the calculator to store that in B. So I'll go back to the home screen, hit store in alpha B, and it will be stored. That is our B value. Then what we're going to do on a test, on the AP test, you have to show the work you're doing. So if we're going to find this value, we will have the area bounded by the curves. Let's pick a different color. Area bounded by the curves is the definite integral from A to B. In this case, A was 0, so we can list it. B was that crazy decimal, and we'll write over here that B is approximately 1.181. That's an estimate. We'll use the actual value from the calculator. And then we have the top curve minus the bottom curve. We know the top curve was this function here. It was x over the square root of x squared plus 1 minus the bottom curve, which was x to the 4th minus x, and dx. Be careful when you have this second function, the bottom curve, that you have it subtract the whole thing. A lot of times a mistake people will make is they'll just do minus x to the 4th and then have a minus x, but you would really, if you were going to simplify, have to distribute that negative. So be careful about that. Just put it in parentheses. I always do when I write it. That way I remember when I'm actually doing the work. Okay, so here is our work that we have shown in the calculator, and we'll find the actual value. So, using the calculator, in y1 I have the top function, in y2 I have the bottom. So if I want to use the notation, I can do y1 minus y2 for this y3. That is the top curve minus the bottom curve. And then I can just integrate y3 on the home screen. So if I go back to the home screen, and I will go ahead and find the math and the function integrator. Let's get this out of the way. And we want to integrate the function. It was in y3, so I'll go y3, comma, for all x. And our lower limit was 0. Our upper limit was b. Just remember what you stored each of these things in. And then when you hit enter, it will give you the decimal. And that decimal answer rounded to 3 decimal places is 0.785 units squared. So the area in between the two curves, I'm going to turn off this. The area in between these two curves, this area here, that area in between the two curves is rounded, or about 0.785 units squared. Remember, it's area, so the units will be squared. Once we start applying these things to actual real-world problems, we'll have actual units and we'll find square feet or whatever the units happen to be. That is all for example 3. Okay, so we can also find area using subregions. Now, when we're given two curves, if it's something easy like the square root of x, that's a parent function. You know what that graph looks like. The other one is x minus 2. That's linear. You know what that graph looks like as well. So I would always make a sketch of those things if it's not calculator active. If it is calculator active, then obviously graph them on the calculator. But making a sketch, based on the knowledge that we have, if this is our x and y axis, the square root of x starts at 0 and does something like this. That's its parent function. That is simple. X minus 2 is the y equals x graph moved 2 to the right, or it would look just like this. And that is a line, whether it looks like one or not, it should be. And we want to find the area of the region R in the first quadrant that is bounded above, meaning that is the top curve, square root of x, and below by the x-axis and the line. So we're bounded by the x-axis, this line, and the square root function. So the area R that we're looking for is this area here. So we want to find this area. Now there are a couple of ways that you can do this. One way, we can't really use the top curve minus bottom curve in this case because that would find everything including this area here. So one thing you could do is find the area from the top curve minus the bottom curve and use or subtract out this little triangle, which that doesn't seem very hard geometrically. You could do that easily. Another way you could do it is we need to find this point because that will be our upper limit of integration. Once we find that, we'll be all set. So this value here is very important because what I can do is find the area from 0 to this value, b, and we can find that algebraically in just a second, from 0 to b under the square root of x. Now what that's going to do, if we have this area total, and then I can subtract out this area here. And what we'll be left with is the area that we're looking for, which is only the area bounded by the upper curve, the line, and the x-axis. So many ways to do this, especially geometrically. Let's go ahead and find the area under the curve of square root of x from 0 to b. In order to do that, we need to know what b is. If it's not calculator active, we'll just solve it algebraically. Solving it algebraically, We will set the two things equal and find out where they are equal. So I have x minus 2 is equal to the square root of x. We need to solve that thing, so I can square both sides. That would be x squared minus 4x plus 4 equals x. Subtract an x. X squared minus 5x plus 4 equals 0. Now we have the parabola equal to 0, and we can factor. This factors to be x minus 4 and x minus 1. Therefore, our solutions, or their intersections, are x equals 4 and x equals 1. Okay, now we have two values for x it comes up with, but we know that's not true. It intersects over here at b. We need to decide which one it is. If I plug in 1 into this equation, I come up with an answer of -1. Now, if that was the case, they should be equal at those places because we set them equal. 1 in here is the square root of 1, which is 1. 1 is not equal to -1, therefore this is not an actual intersection. Let's try 4. 4 into this equation comes up with a value of 2. 4 into this equation comes up with a value of 2, so that is the actual place where they intersect. So, this b value is 4. Okay, now, this triangle in question here, we can find that area. We'll subtract that out from the area under the square root curve. So we are going to find this total area and then subtract out the triangle. The total area, let's get rid of this. The total area under this curve would be the definite integral from 0 to 4 of the square root of x dx. That's the total area. And now we need to subtract out the area of that triangle. Minus the area of the triangle, which is 1/2 the base, which is 2, multiplied by the height, which is the value of this, which is 2. And that will give us the area under the curve. So, you can do that in the calculator, or you can do that by hand. This, obviously, is 2. So, it is equal to. The antiderivative of the square root of x is 2u to the 3/2 over 3, evaluated from 0 to 4, minus the area of the triangle, which was 2. So area under the square root curve minus the area of the triangle. That will give us what is left, which is the area bounded by the square root function, the line, and the x-axis. So let's simplify this here. Alright, fundamental theorem of calculus we're applying here, so I plug in 4. Probably can't see that. So it would be 4, I don't know why I put a u there, I'm so used to doing a u substitution. Try it again, 4 to the 3/2 power, that is the square root of 4 cubed. So this is 2 multiplied by the square root of 4 cubed over 3, minus 2 multiplied by the square root of 0 cubed, which is going to be 0. So this is going to actually cancel out and be 0. All of that minus the triangle, fumble on the snap, minus the area of the triangle, simplifying, 2 multiplied by this, 2. 4 cubed, we can take 2 4's out since it's a square root, so it would be 4 square root of 4 over 3, minus 0 minus 2. Simplify. Square root of 4 is 2, times 4 is 8, times 2 is 16, that is 16 over 3. Minus 2, let's write it with a common denominator. Multiply by 3, that would be 6 over 3, which is a value of 10 over 3 units squared. It's an area, units squared. That is 10 over 3. And all of that math you are probably very familiar with. The major idea that is new for you now is we're finding area bounded by specific functions. The x-axis, or y equals 0, the line, and the curve, square root of x. And we did that using our knowledge of definite integrals, along with our knowledge of geometry and subtracting out that triangle. All right, let's move on to the last question. All right, now, a major idea of what we've done up to this point is the top curve has to be always greater than or equal to the bottom curve. Now, as you know, that is absolutely nonsense because that doesn't always happen. But we can take care of that problem. There are two ways to do so. One is if it's calculator active, we will take the absolute value of the top curve minus the bottom curve. It's not going to matter which one you pick for the top or the bottom. It does not matter because when you take the absolute value, that difference is always going to be positive. So this, if it's calculator active, will be very easy. The area is equal to the definite integral from a to b of the absolute value of f of x minus g of x dx. Simple. If it's calculator active, it's not a problem at all. You have two curves. Doesn't matter what one's on top and what one's on bottom. If it's not calculator active, then what you're going to have to do is break up these curves into piecewise functions. For example, if you're looking at this example here, you will have to break it up into a top curve and a bottom curve and use the appropriate functions. So if I'm integrating from a to b, I will have to break it up at this point. Top curve, bottom curve. And then I'll have to break it up at this point. And my top curve changes, and my bottom curve is the opposite. And then you'll have to integrate from this point to b, which will be the top curve and the bottom curve. So you're going to end up having to break it up into three different definite integrals if it's not calculator active. But once again, if it's calculator active, do in the calculator the absolute value of f of x minus g of x, and life will be grand. Just remember, if it's not calculator active, you have to break it up into top curves and bottom curves. So, doing so, let's take a look at an example. We are given, it says, for example 5, find the area between or bounded by the curves sine of x and cosine of x from 0 to pi over 2. So what we're finding, if it's calculator active, is the area. We don't even care which one is the top, which one is the bottom. We just simply need to integrate from 0 to pi over 2 of sine of x minus cosine of x, and it's the absolute value of that, dx. So doing so, what your y equals is going to look like we will just type in the function. It's the absolute value. It's under math, arrow over 1 to the right, absolute value. Sine of x minus cosine of x. And close your parenthesis. If you look at the graph, you'll see that it's an actual absolute value graph. Where it was negative, it's flipped positive. If it was positive, it stays positive. You'll remember those from our transformations in pre-cal. Now we want to integrate from 0 to pi over 2. So I'm just going to make sure my window goes from 0 to pi over 2, or somewhere outside of that. Here is the window that we are finding the area of. We're just going to find the area under the curve from 0 to pi over 2. Here we go. Second trace. and lower limit is 0, upper limit type in pi over 2. Do not type in 3.14, that is garbage. And you can see using the calculator that we have an area of approximately 0.828 units squared. Now, that was calculator active. It's easy in the calculator. Use the absolute value of one curve minus the other curve. If it is not calculator active, we need to find out where sine and cosine are equal. Let's go through that process. So, if I'm going to find out where sine and cosine are equal, sine of x is equal to cosine of x. And remember, we're only worried about 0 to pi over 2. So on the unit circle, 0 to pi over 2. Where are sine and cosine equal? And you know the answer, or at least should. Humor me and say that you do. It's pi over 4. At pi over 4, sine and cosine are both square root of 2 over 2. So using that knowledge that you already have, we know that we have a change in top curve and bottom curve at this point. If I sketch what these things are what they look like in the first quadrant, sine starts here. Wow, that's devastating. That was actually cosine. And sine starts at the origin. We know that starting out from 0 to pi over 2, if this is pi over 2, cosine starts out as the top curve. That's a horrible sketch, but you get the idea. Cosine is higher than sine. So from 0 to pi over 2, there's only one place where they change, and that's at pi over 4. So what we're going to have to do is integrate from 0 to pi over 4, and cosine is the top curve until their intersection. So it would be cosine of x minus sine of x dx. And after pi over 4, from pi over 4 to pi over 2, we know that sine is the top curve. So we will have plus the area from pi over 4 to pi over 2 of the top curve, which is now sine of x, minus the bottom curve, which is now cosine of x. And of course it's a dx. Now this will be the same area that we came up with using the absolute value function. It is simply a piecewise function for absolute value. That's something that we've talked about. I can break this absolute value up into these two things, two pieces. Finding the value of this will give you the same exact value of that. We're not going to go through the actual calculations for the fundamental theorem of calculus and your definite integrals. Those seem pretty trivial at this point. I'm sure you're good, or should be good, at finding those values. So we'll come up with something around 8 units squared. And I would imagine that that 0.828 is actually some value in terms of pi.